Next, we move on to the graph abstraction.
At the graph level of abstraction, you could create customized modules in the form of directed X-link graphs of stage nodes from the previous level of abstraction. In addition to the brand new graphs that you could create using the graph construct, we also offer a number of built-in graphs. These built-in graphs include different image feature extractor encoders and transformer encoder, as well as loss, evaluation, and multiplexer graphs.
The graph construct can be used to create graphs of stage nodes. This construct comes with 4 parameters that define the graph corresponding to this module. These 4 parameters are in nodes, out nodes, nodes, and edges. Nodes specifies the list of the internal stage nodes. In nodes specify the list of the input stage nodes. Edges parameter is the list of the edges connecting the nodes of the graph. Finally, out nodes parameter is the list of the output nodes of the graph. In terms of the nodes of the graph, we have 3 parameters: in nodes, out nodes, and nodes. And you might ask how they interact with each other. In nutshell, a node of a graph could be either an input node for the graph or an internal node for the graph. If it is an input node for the graph, it has to be listed as one of the nodes in the inNodes parameter. And if it is an internal node for the graph, then it has to be listed as one of the nodes in the nodes parameter. Any of the input nodes or the internal nodes of the graph could be one of the output nodes of the graph. Therefore, the outNodes parameter is the list of the names of the nodes that you want them to be the output nodes of your graph, and there could be either part of the inNodes parameter or the nodes parameter. First, we add input nodes for our graph using inNodes parameter. InNodes parameter is optional. A graph without any input nodes is a source graph. Here we specify the first input node. Note that the order of the input nodes matters. It is because in the next level of the abstraction, when this graph module is being used as a node in the metagraph, then the object received on the first incoming edge of that node will be passed to the first input node here, and also the object received on the second incoming edge of that node in the metagraph will be passed to the second input node here, and so on. When you want to add a new input node, you have 2 options. The first option is the stage-based config, and the second option is just to provide the name of the input node via the string option. If you go with the second option, then you just need to provide the name for the input node, and the system will create a bypass input node with the name that you provided. Bypass nodes are special nodes in the sense that if a bypass node is connected to a destination node, then that destination node can only have a single incoming edge, which is the edge coming from the bypass node. Here we choose our first input node to be a bypass node by providing its string name to be input1. For the second input node, we want to go with the stage-based config. Choosing a stage-based config, then from the drop-down menu, we have several options. The first option is to choose one of the built-in stage modules, which are bypass, input mapping, and multiplexer. The second option is to create a brand new stage module using a stage config. And the last option is to choose a module from our personal stage module library. Currently, demo stage is the only module in our stage module library. For the second input, we want to create a brand new stage, therefore we choose the stage config. We set the name of the second input to be input2. Next, we specify this stage to have a block with a single linear layer with the input size of 8 and the output size of 16. We save our graph in our graph personal library. Next, we switch to the graph interface in order to further modify our graph. The canvas has 2 nodes. Each node on canvas comes with 6 buttons on its right-hand side. The rightmost button is the minus button that removes the node. The second button from the right is the setting button that allows you to modify and inspect the parameters of the node. The third button from the right is the rename button that renames the node. The fourth button from the right is the connection button that allows you to change the order of the incoming and outgoing edges of the node. The help button is the leftmost button. The second button from the left is the mode button that allows you to change the mode of the node. As you can see for these two nodes, the selected mode is the input node. In addition to changing the mode of the node, the mode button allows you to change the order of the input and output nodes of the graph. Because these two nodes are the input nodes, the information regarding the order of the input nodes of the graph being presented. In particular, graph input 0 refers to the first input node of the graph and it is set to input 1, and graph inputs 1 refers to the second input node of the graph and it is set to input 2. There are four options regarding the mode of the node: internal node, input node, output node, and input and output node. Each mode is being color coded. The color for the input mode is blue, and that is why the color of these two nodes is blue as well. Next, we change the mode of the node to internal, which changes its colors to white. As you can see, changing the mode of this node to internal, the information regarding the graph input nodes disappear. Now the node input 2 is the only input node for this graph, and graph input 0 is being mapped to input 2. Changing input 1 to an input node changes its color back to blue. The color for the output mode is purple. As you can see, making the node input 1 to an output node, the information regarding graph output nodes being shown. Here the graph has a single output node and graph output 0 is being mapped to input 1. Also, a node at the same time could be among the input and output nodes of the graph. The selected color for this mode is green. Let's switch back the mode of the node input 1 to input only. Now the first input node of the graph is the node input 2 and the second input node of the graph is the node input 1. We change their order. Next, we use setting button to inspect the parameters of the nodes. We add a new internal node to our graph by dragging the stage config from the left sidebar and dropping it on the canvas. Clicking on the rename button, we rename this node to node 3. We add an edge from input 1 to node 3. Because input 1 is a bypass node, node 3 cannot have any other incoming edges. The block of the stage node 3 will have a single linear layer with the input size 32 and the output size of 16. Next, we add another internal node to our graph. This time we drag and drop the demo stage from our stage personal library. We rename this node to node 4 and add edges from node 3 and input 2 to this node. Clicking on the connection button, we see the list of the incoming edges for this node. In general, the order of the incoming edges for the nodes matters. Input 0 refers to the first incoming edge of node 4 and is being mapped to node 3. And input 1 refers to the second incoming edge of node 4 and is being mapped to input 2. However, for node 4, which is an instance of demo stage, the aggregator is an addition layer, which means that the order of the incoming edges for this stage node doesn't really matter. So far, our graph doesn't have any output node, but we want to change it. Therefore, we click on the mode button of node 4 and change its mode to be an output node. Next, we switch to the config interface and observe that all the changes that we have made in the graph interface being successfully transferred to the config interface. Awesome! We reviewed how to create a customized graph module. Now we want to review the built-in graph modules. Let's start with ResNet 34, which is an image feature encoder. Image tensors having the 3 channels of red, green, blue, we set the input channel size to be 3. The graph corresponding to ResNet 34 feature encoder has 5 stage nodes. If you are familiar with the architecture of ResNet 34 feature encoder, you know that the ResNet 34 actually has 5 stages, and these stage nodes here refers to those stages of ResNet 34 architecture. Let's see what's happening inside stage 1. Each node on the canvas comes with a set of parameters, and it is useful to be able to quickly figure out that which ones of these parameters are set and which ones of them are not set. A quick way to do that is just to hover your mouse over the parameter, and if the color of the parameter doesn't change and stays gray, then it means that that parameter is not set. But if the color of the parameter changes to blue, it means that that parameter is set. For example, here device is set, aggregator and pre-block are not set, and block is set. Okay, we know that the block parameter is set. Now the next step is to figure out what is happening inside this block parameter. This block has 3 layers in its main branch, and it doesn't have any layers in its residual branch or any post layers. The first layer is a convolutional layer with the input channel size of 3 and the output channel size of 64, and its kernel size is 7 by 7. Its stride is 2 by 2 and its dilation is 1 by 1. The second layer is a ReLU layer, and the last layer of the block is a max pooling layer with the stride of 2 by 2 and the kernel size of 3 by 3. Okay, now we know what are the layers inside the stage 1. Let's go for the other stages. For stage 2, only block is set, but for the other stages, both pre-block and block are set. Next, we expand the block parameters of all of these 4 stages in order to compare them to each other. This gives us an overview of the overall architecture of ResNet 34 backbone. For example, it tells us that the channel size of the feature map generated by the stage 2 is 64. The channel size of the feature map generated by stage 3 is 128. By stage 4 is 256, and by the last stage is 512. This is great. We are able to figure out the exact architecture of ResNet 34 backbone using the graph interface. But that is not the end of our journey with this graph configuration. Essentially, we can modify this graph architecture exactly to our needs. For example, now what I want to do is to remove the last stage of this graph and modify the stage 4 of this graph. We make stage 4 to generate the feature maps by channel size of 512 instead of 256. Next, we add this modified ResNet 34 backbone to our personal graph library so that later, for the next level of abstraction, we could use this graph to create more complex networks. Great. Now this modified ResNet 34 is part of our personal graph library, but we made a mistake with the name. It is not actually a ResNet 18, is ResNet 34. So we changed the name from ResNet 18 smaller to ResNet 34 smaller. Okay, we are now in the config interface, and we could inspect the parameters of this modified ResNet 34. For example, when you look at the nodes parameter, unlike the default ResNet 34 that has 4 stage nodes as part of its internal nodes, this modified ResNet 34 has only 3 stage nodes because we removed the last stage, as you remember. We want to make a final change to our ResNet 34 smaller. In the default ResNet 34, all the stage nodes except the first stage node are actually the output nodes. What it means is that when the graph execution engine wants to populate the output object for this graph, it collects the feature maps from all the output stage nodes and then output them. However, what we want for this smaller ResNet 34 is to just output a single feature map. And because of that, we change the list of the output nodes for this graph. In particular, we remove stage 2 and stage 3 from the list of output nodes. Going to graph interface, we see that the only purple node is stage 4. Perfect, we are done with our ResNet 34 modification. The main building block of large language models is their transformer encoder. In our platform, we represent transformer encoders as graph constructs. The built-in transformer graph presented here allows you to create a variety of different types of transformer encoders. Essentially, what we are doing here is that we collect all the parameters that define the exact architecture of the transformer encoder that you want to create, and then under the hood, we create the graph of the stage nodes that actually realize that functionality and that exact architecture that you are interested. Every time that you select values for the parameters of transformer encoder and you click on the graph button, the backend validates those parameters. If the values of the parameters are not valid, then the backend will give you an error message with the information about the condition that has been violated. This feedback from the system is useful since it guides you step by step on how to set the values for the parameters of the config that you want to realize. We demonstrate this process here for transformer encoder. Clicking on the graph button for the first time, the system is telling us that we need to set the embedding dimension value. So let's do that. We set the embedding dimension to 128 and we click on the graph button for the second time. This time the system complains about the embedding config that has not been set. So that's what we do next. The embedding config configures the embedding layer, which is the first layer of the transformer encoder. We set the embedding config and we click on the graph button. This time the system is telling us that we need to set the out channels parameter of embedding config. We set out channels to 64. Next, the system complains about the vocab size, which is supposed to be a positive integer, but currently is set to -1. In order to fix it, we set it to 30,000. The embedding dimension and the out channels parameter of the embedding config are supposed to be equal, but that is not the case right now. In order to make them equal, we change the value of out channels from 64 to 128, and that will fix the issue. After fixing the out channels parameter, now the system is asking us to set the config for the attention layers of the transformer blocks of the transformer encoder. After setting the attention config, now the system complains about the number of the heads for the multi-head attention config. We set the attention layers to have 4 heads. The next parameter that we need to set is the number of the blocks of the transformer encoder. Here we select the transformer encoder to have a single block. We set the context window of our transformer encoder to 512. Setting values for the parameters RMS norm attention feed forward and RMS norm feed forward is optional. If you don't set values for these parameters, then the default config will be used to instantiate them as part of the transformer encoder. The RMS norm attention parameter specifies the configuration for the RMS normalization layer before the attention layer. The feed-forward parameter determines the configuration for the point-wise feed-forward layers of our transformer blocks. RMS norm feed-forward specifies the configuration for the RMS normalization layer before the feed-forward layer. The rotary embedding config is optional and you only need to set it if you want your transformer encoder to have positional rotary embeddings. Finally, we have set all the required parameters for the transformer encoder, and now the system doesn't complain anymore and show us the graph representation of the transformer encoder that we wanted to create. We see all the stage nodes and the connections between them that form the transformer encoder. The only input node for our graph is the embedding node that takes the input token indices and generates embeddings. The embeddings generated by the embedding node goes to the RMS norm node as well as the addition node. The normalized embeddings by the RMS normalization node are being passed to the multi-head attention node. The embeddings generated by the first addition node are being passed to the second normalization node as well as the second addition node. The normalized embeddings by the second normalization node will be passed to the pointwise feedforward node. Next, we inspect the parameters of these nodes. Please note that while inspecting the parameters of these nodes, you have the option to change them in order to create more customized transformer encoders. The input embedding node has a block with a single layer, which is an embedding layer with the vocab size of 30,000 and the embedding size of 128. The RMS normalization node has a block with a single layer, which is the RMS normalization layer. The attention node has a block with a single layer, which is a multi-head attention layer. The two addition nodes come with blocks that have a single addition layer. The feedforward node has a block with a single layer, which is a pointwise feedforward layer. As we mentioned before, you have the option to modify the parameters of the nodes. For example, in the case of the pointwise feed-forward layer of the transformer blocks, by default, the dimension size of the hidden embeddings is equal to 4 times of the embedding dimension of the transformer encoder. That is why here the hidden channels is equal to 512, which is 4 times of 128, the embedding dimension of the transformer encoder. Having a direct access to the hidden channels parameter of the pointwise feed-forward layers of the transformer blocks, you could change them in order either to increase or decrease the capacity, and the number of the parameters of the feed-forward layers of the transformer blocks that you want. Switching to the config interface, we are still able to inspect the parameters of the transformer encoder graph. Next, we create another transformer encoder, which is similar to the transformer encoder that we already created, with the only difference that the number of the transformer blocks for this encoder is 4 instead of a single block. Having 4 transformer blocks, this encoder has 4 times number of stage nodes compared to the previous encoder. Right now, the only output node for this transformer encoder graph is the output addition node of the last transformer block of this encoder. But what we want to do next is to include the output addition nodes of the second and the third transformer blocks as part of the output nodes of this graph too.